recording? Great. Hi, everyone. Hi, all the audience. Hope you all can hear me well. Thanks to you all for joining the IEEE CIS webinar today. My name is Jialin, postdoc research associate at Queen Mary, University of London. After the success in the game Go by Google DeepMind, I noticed on social network that people were wondering what would be the next challenge in AI. Personally, I would say Mahjong, as it is a multi-agent game with partial observability and has various ways of winning with different final outcomes. Also, during the game playing, the players may build implicitly an alliance and break it at any time. Another reason that I suggest Mahjong is because it is a common game in my country, but in Europe, Mahjong is less common, not like the game Go, which is well known in many countries. My former colleague and friend, Dr. Véronique Ventos, is more interested in the game Bridge, which is quite popular in Europe and seems to be more difficult than the game Mahjong. I have the honor to invite Dr. Véronique Ventos to give a webinar today about her recent research and project AlphaBridge, which is set up when she joined me and joined INRIA France in 2015. By the way, she is not only an excellent researcher, but also a bridge player. Before we start, I would like to remind you that you can ask questions either using audio or text at the end of the talk. So Véronique, it's your turn now.
Yes. First of all, thank Jialin for setting up this webinar and for being so enthusiastic about my research on Bridge. I am a serial researcher in artificial intelligence at Paris Saclay University and also an addict bridge player. So 2 years ago, I decided to combine my two passions, AI and bridge. It was difficult at first to convince my fellow scientists that bridge was much more than just a game and that solving bridge will be a huge challenge for AI. But here we are with several top-level scientific collaborations and many exciting challenges to address in the years to come. The first question is, why are AI researchers interested in games? First of all, they are much easier to understand and to model than real-life problems, since they have limited number of simple rules, they benefit from in-depth human analysis over time, etc. Games then provide an excellent field of experimentation for systems that can later be used in the context of real applications. AI designed to solve games always have multiple applications in different areas. For instance, IBM Watson, well known for its success at Jeopardy, a quiz game, is now used as a healthcare consultant. In the last decades, design of champion-level systems dedicated to a game AI, were considered as milestones of AI. Because of its complexity, bridge is the last mind sport resisting AI. I will start with a brief description of bridge and its challenge. Then I will present our works regarding the boosting of an existing bridge AI. The third part is dedicated to an introduction of our AlphaBridge project. I will present in this part an overview of our current and upcoming works. Before introducing bridge and its challenges, let us begin with a quick overview of the most well-known game challenges. The challenge that got the best media coverage was probably the one related to chess, when Deep Blue beat the world champion Garry Kasparov. However, it has to be noted that Deep Blue did not use any AI or machine learning technique. Its victory is due to the use of a supercomputer entirely dedicated to chess, coupled with human expertise. Once again, in 1988, brute force and human expertise allowed to solve Connect 4, The first game where machine learning techniques were efficiently used was backgammon, where the machine reached top level thanks to neural networks. Finally, in 1994, the checkers, also called English draws player system Chinook, became the first computer program to win a world champion title against humans. More recently, despite increasing processing power, a major challenge of artificial intelligence was to design a computer program reaching the level of a human Go grandmaster. Everybody has certainly heard of AlphaGo that won this challenge. AlphaGo uses different machine learning methods such as deep learning, reinforcement learning. The early versions of AlphaGo, AlphaGo, and AlphaGo Master used human expertise to train the system. The last version, AlphaGo Zero, that greatly outperformed the others, only used the basic rules of the game as an input. The Go challenge having been addressed, researchers turn to other games that have different types of difficulties. First, poker is often presented as a new challenge for AI. Here, I will only mention StarCraft, a video game that many researchers study, but whose issues like real-time management are quite remote from bridge issues. In January 2017, the Poker AI Laboratories won a heads-up no limit Texas Hold'em poker event, but we can notice that this simplified version of the game is reduced to a two-players game like Go or chess, which is not possible for bridge. Laboratories and its DeepMind equivalent DeepStack have better and better results against champions. This success has not yet happened with regard to the game of bridge. Our conviction is that defining a top-level bridge AI will be an important step between AlphaGo and a general artificial AI, since bridge robots are far from best human players. It is quite similar to Go programs before 2006. But what is bridge exactly? Here is, I guess, what people think bridge looks like. This is the reality in 2017, younger and more modern. And there are yearly high-level competition as shown in these pictures of human world championships. I will not deny the game is tough and that it takes a little time to apprehend, but I will try to give you the basics without getting too boring. Bridge is a card game with 4 players, each player having a partner and 2 opponents. More precisely, Bridge is a trick-taking game played with 52 standard cards opposing 2 pairs of players. It is a stochastic game since cards are dealt randomly to the 4 players. It is an incomplete information game since players do not have common knowledge of the game being played. Each of them only sees his hand, that is to mean the 13 cards he has in his hand. A board is the set of 52 cards distributed in 4 hands with additional information used for scoring. A bridge match is composed of n boards. For each board, there are 2 successive steps that I will briefly describe. The first step is called the bidding phase, can be seen as a coded language used by players to pass information to their player partner about the hand. The goal is to reach an optimal contract, the contract specifying the minimum number of tricks among the 13 to be won in the second phase. The second phase is called the card play. The goal is to fulfill or to defeat for the opposite side the contract reached during the bidding phase. Now, I will present a joint work with Yves Costel, Olivier Teto, and Solène Tepo-Ventos, which consists in adapting to bridge a recent method using for boosting previous games AIs. The method is called the seed methodology and can be applied on stochastic computer programs. A stochastic computer program uses a pseudo-random number generator initialized with a number called a random seed. If the seed is fixed, the AI becomes deterministic if the AI has clean seeds. Then, the different versions of the AI can be compared in order to find best seeds for a particular game. It has been empirically shown by Tristan Cazenave, Jialin Liu, and Olivier Teto that the seed methodology optimized the performance of several games like Atarigo, Domineering, Racetracks, and even in an incomplete information game like Phantom Go. But is it the case for bridge? Our goal is to adapt the method to bridge AI and to check whether performance can be boosted. The following screenshot represents a complete vision of a board. The question is, where are used the simulation in a computer bridge AI? The player's vision on the same board shows that we have 3 hidden hands. Simulations are done in order to handle this incompleteness of information. More precisely, throughout the game, the hidden information is reduced, the incompleteness decreasing either in a certain manner, for instance by cards put on the table, or with a high probability, for instance by information exchanged during the bidding step. The main goal of each player consists in rebuilding the hidden hands in order to make decisions. More precisely, Monte Carlo simulations are done when rules of the system are not sufficient to make a decision. For instance, when you must choose a contract during the bidding step. The program produces repeated random samples of the 3 hidden hands according to the context and consider their average score in making a decision. More precisely, the score is computed using a double dummy solver, which maximizes the number of tricks for each side in a simplified version of bridge where the final contract is given, the 4 rounds are known, and every player plays optimally. For instance, on this board, we obtain the maximum number of tricks won by each side for every possible contract, when all 4 players know the emplacement of the 52 cards and each player plays optimally. Here are the 3 steps of the evaluation. In step 1, there is generation of possible hidden hands. We then have complete information. The 4 hands are known. We can use the double dummy solver in the step 2, which provides a score for each generated board, and then we compute the expectation value of the score. This truth thread provides us the evaluation function we will be used in the following. We have chosen to boost Bridge AI WBridge 5 developed by Yves Costel. Here we can see the screenshot of this AI. And the first step of our work was building a matrix with the results of matches between the various deterministic versions of WBridge 5. A match is composed of 64 boards, since it is the usual size used in computer bridge competitions, and the score of a match is equal to the sum of the scores of each board in international match point scale. We build a matrix in order to compare 40 seeds, and note that the score is computed using the double dummy analysis. Here is the results. I just focus on the worst and the best seed. The worst seed is a seed 22, and the best is the seed 39. And we see that there is a won matches rate of 56.4 for the best seeds, and only 41 for the worst. We then made a cross validation where we can see that the performance that improves with larger sub-matrices. So we decide to make empirical validation by playing matches between opposing the different tested seeds. I will skip half these experiences in order to reach the comparison between the best seed and the whole seed that had been randomly chosen in the earlier version of AlphaBridge 5 by Yves Coster. We can see that the seed choice has a significant impact on the performance, although its extent 0.1 EMP per board is hard to measure for a non-bridge player. In September 2016, we had the first opportunity to test our approach in a real-life event by involving the boosted version of AlphaBridge 5 in the World Computer Bridge Championships that stay in Wrocław in September. We can see here the results. And finally, AlphaBridge 5 won the championship by a small margin, 0.1 EMP per deal, that incidentally correspond to the measured improvement our seed approach brought to the bridge robot. Other work carried out together with Yves Coster, Nicolas Galichet, and Olivier Teto have adapted to bridge a UCB approach based on the works of Jialin Liu, Olivier Teto, and Tristan Cazenave. Our algorithm allowed us to find a new, better seed that has been used in the World Championships in Linz in August 2017. These works are currently being published. AlphaBridge 5 again won the championships, winning the final with a small margin of less than 6 IMPs. Those works were carried out within a framework where robots face other robots. Our goal is now much more ambitious because we want to build a system that will outperform the best human players. A good bridge player has to do some complex reasoning. Even if he needs to count and sometimes use simple probability, the skills that are necessary to be a champion of bridge are closer to those of a doctor than to those of a mathematician. At this time, robots are far from the best human players. We are in the same situation as Go was before 2006. The AlphaBridge project that I started 2 years ago consists in building a bridge AI that will outperform human champions. The main difficulties inherent to bridge are the following. We are in a case of incomplete information. The game is both cooperative with the partner and non-cooperative, if possible, with the opponents. Reasonings of different types have to be set up. Bridge needs explanation from the players at some point, bidding, carding, and some psychological factors have an influence on bridge decisions, partners, and opponent approach of the game, their level, if they're optimistic or not, etc. And lastly, human expertise is nothing else. But it is also great to work on bridge because rules are simple and broadly known. The game is sequential and easily modelizable. The scoring is incremental according to the number of tricks. There is a huge amount of data in standard format, but they still require an expertise depending on the task. At last, the duplicate scoring of the game consists in comparing the results of pairs playing the same hand separately. This method removes the element of luck in getting good cards when comparing players and thus helps to isolate the role of skill in the game, and it is not the case for the poker, for instance. Besides, we can select data coming from this played by top-level humans, since most competitions are recorded via a website called Bridgebell Online, whose picture you will see in the bottom right of the photo. Here are all the information that we can work on: bidding, played cards, score, and also expert comment. And here is the same deal played at another table. We have the same 4 hands, but different players, different bids, and different card play. It's very interesting for us to compare the different manner to play with the same cards between several champions. AlphaBridge is composed with different modules from different AI paradigms with different levels of representation, use or learn a knowledge domain. We have collaborative components, agents. Here is an incomplete list of areas involved in the different modules: reinforcement learning, probabilistic programming, planning in Markov decision process, deep learning, etc. I have been lucky enough to bring together top-level researchers to work on Project AlphaBridge. Bruno Bouzy, Olivier Teto, and Tristan Cazenave are renowned for their research in computer games and have all played a central role in the solving of Go. Céline Rouverer is one of the best researchers in the inductive logic programming area, and I hope our host today, Jialin, will soon be convinced to collaborate with us. 5 students from the prestigious École Polytechnique are also involved in this project, and a special mention to scientists from other areas, such as particle physics, psychology, or neurobiology, who are also actively participating in AlphaBridge. Moreover, I want to thank bridge players that help us with their knowledge. And for instance, Jean-Baptiste Fantin, Jean-Christophe Quentin, Jean-Pierre Desmoulins, Philippe and Bénédicte Cronier have started to work with us. I will not get into each model's details, but would like to insist on the need of explanation. Indeed, the game of bridge is a great example of an application needing more than black box approaches. At some point, players must explain their actions. It is just part of the game. You cannot play if you don't explain your actions to your opponents. Generally, the need for explanations is a great upside for machine learning systems. For example, it allows to track mistakes more easily, since the system can explain if you understand or not why you succeed, why you fail, if I can trust the system on some points or not. One of our models is related to the symbolic paradigm of AI, called good old-fashioned AI, but we think that it will soon come back into still we believe in its modern version. In this paradigm, objects are described by attributes participating in relationships, action, and events, and the solutions are human readable. More precisely, the chosen framework is inductive logic programming, where formalism is written out to allow reasoning about relational structure of the data. For instance, links between web documents provide propagation about the topic. It is just as well because bridge is relational. There are some existential reasoning, links between cards, and etc. Works are being carried out with Swan Legras and Céline Rouverol. The main goal was to learn a set of rules understandable for humans in order to provide an adaptive system and to automatically and incrementally update a set of rules used by the systems. We have created an interface where experts tag their decisions in order to obtain our learning set, that we also use bridge-based online IDs as an entry. So we want to express the rules that several experts have to take limit decision. For instance, should I open or not end with 11 points when the rules state that we should open with at least 12 points? Numeric modules that interact with the symbolic module are also planned. They are currently in implementation. They are dedicated to tasks at which they excel, such as pattern recognition, for example, the imitation of the first card play, according to the bidding sequence. Modules coming from the computer games community like tree search and CTLs will also be central in the architecture. Our goal is to reconcile different approaches and to set up collaboration. The collaboration can, for instance, to use symbolic knowledge to make an initial guess at the concept, description, standard neural network approach, making a random guess. We want to use the better of both approaches. They are not as efficient for the same task. We hope that AI winter will not come back. And to conclude, we think that our success in the bridge challenge would have a huge impact on different areas, healthcare or finance to start with, because in everyday life humans have to make decisions in a context of incomplete information coming from different sources, and humans have to explain the rationale for their actions. Thanks for your attention, and feel free to contact us. Collaborations and ideas are really welcome.
Okay, can you hear me well, Véronique?
Yes.
Great, thank you. I just unmuted myself. Thanks for the excellent talk. I want to do some screenshot during your presentation. Then I was so concentrated in your talk that I forgot. So now is the question time. I've seen that Junkai Li has raised a hand. So Junkai, I will unmute you to ask question.
Okay.
Junkai, can you?
Hello, can you hear me?
Yes, hello.
I would like to know if there are any enterprise which are focusing on this area.
No. In fact, enterprise on bridge just study robots who plays with human. It's a particular study because the goal is not to defeat, to reach the level of champion, but just to be good partner for human. And in such enterprise, I think the more study the possibility to be related to human players, but against two robots. So I did not know enterprise that works on really AI approaches for bridge.
So enterprise like AlphaBridge, they don't have intention to work on such a project?
No, in fact, AlphaBridge have a set of rules, but the set of rules is designed by a human, and it is there is no machine learning for the moment, but they can improve their system with such approaches. But at the moment, the set of rules is just defined from human expertise, and when people will play against robots, and if they see that robots make some faults, they send an email, and then they add new rules. But as I know, there is no machine learning module.
Okay, thank you for your answer.
Thank you.
Okay, thanks, Junka. I will mute you. We have another question from attendants that I'm not able to pronounce the name correctly, so I will just unmute you and you can introduce and ask questions by yourself. Thank you. I think that's Oysten Schooling Johnson. You are unmuted. You can ask question now. Hello.
Does this work?
Yes.
Do you hear me now?
Yes.
Okay. This is Øystein Schønning Johansen from Norway. First, just an elementary question. What about the bidding phase? Are you making an agent both for the bidding phase and the card playing phase of the game, or is it both?
Sorry, can you speak little louder, please?
Sorry.
I didn't understand the question. Sorry.
Are you building an agent both for the bidding phase of the game and the card playing game?
Yes.
Phase of the game. Yes. Okay.
Yes.
So,
yes.
Then there are some standardized bidding patterns like 2/1 and SAYAC and all these popular ones from. Isn't it more like a rule-based system for the bidding?
In fact, we consider that for the bidding we will use standard LaHDAK library or system like stake for America, for US, or SAFE for French, etc. We assume that the bidding system will be given as an input, like for human player. When you play, you receive the system, and we assume that the system will be given to our bots, and the goal is to make automatically the inferences like a human.
Okay, so even though the computer knows that he is about to use 2/1 or SAYAC or whatever, it still has to make some logic decisions.
Yes, okay. Like a human.
Yes, but, exactly. Good.
Okay.
Thanks.
Thanks.
Okay, thank you. Sorry, it's a little bit. There is a little bit delay when I mute and unmute people. So I'll see that Robert Trostad want to ask a question, and now Robert, you are unmuted now, so you can ask. So Robert, please ask your question now. You are unmuted.
Yes.
Hello.
Hello.
Yeah. I will test this person.
Yes.
Hello. Oh, okay. I can see this person's question by text, so I will read the question.
Okay.
This is question. I will read from now. Hi, thanks for the talk. It strikes me that one weakness of current bridge programs, for example, GAB, is that double dummy approaches assume the opponents play double dummy. For example, the computer may defend against a squeeze that is visible double dummy, but the declarer would never play for. Or it may fail to lead small towards a singleton K because double dummy the opponents would never duck. What seems to me to be the problem is double dummy solvers don't take into account that the opponents have incomplete information. Have you considered how to build a system that capitalized on the opponent's imperfect information? For example, not just double dummy solving. Véronique, if due to my pronunciation problem, if the question is not clear, you can read the question in the question part.
The question, thank you. The question is really interesting. It's a very good point, and in fact, it is really a bridge question. It's true that the double dummy analysis is actually the only evaluation function we have, but in one module on which we work on as the goal to how can I say that, to improve this evaluation function, since the double dummy analysis does not reflect the reality. In fact, it is more easier to understand for bridger that when you make a simulation, the double dummy solver will say that one board will provide 10 tricks that non-bridge player will make 10 tricks, because it's assumed that you will take a very, very bad line for a player. In fact, we must surpassing the double dummy analysis by defining a better evaluation function. It's really a good part of the project. I didn't present it here because I think it needs some knowledge about bridge, but it's sure that the double dummy analysis should be improved in order to take in account some probability. For instance, it will say that you will make your contract, but no expert will make the contract because it will play according to probability, and it don't see the three hidden hands. So some boards are counted as good to take the decision, but they are bad, and some others I consider it as bad and they are good. I will be happy to discuss this point with the persons if we can if she can contact me, or it will be very interesting to have a discussion about this.
Okay, thank you, Véronique. Here is another question from Paul Grink. I'm not sure if you addressed that. Will the bidding system have input from human experts, or will it be based on AI alone? So, what I will understand, yes, please.
The question is about how the bidding system
Yes.
will.
Does it have input from human experts, or will it be based on AI alone?
No, in fact, the goal is not in the first part to improve a human bidding system. We will use a human bidding system and learn the robots to efficiently use that, because I think it's not fair for a human if we want to make a fair challenge against them to use a very complicated bidding system. And besides, there are some rules. You are not allowed to use two artificial systems during the competitions. So the goal is not to produce a good bidding system, but to use classical systems and to defeat humans with their systems.
Okay, thank you, Véronique. Let me see if there are additional questions. Oh, Paul has answered. Thank you. Okay, thanks for the answer. And actually, I remember in the past computer Go competitions in the CIG conference, there has been once that people have suggested to organize competition with computer Go and the human player in a team, which means that the program can suggest moves, and the human player will decide the actual move. And I don't remember if the competition has been organized or not at the end. But what I understand is that in the current Bridge World Championship, there is only computer programs to compete with each other. There is no human intervention at all, right?
Yes.
Okay, great. Thank you. Thank you. So, yes, please.
Sorry, yes, it's very interesting because we have another module, the goal of which is to help human to play and not to play. It's a part of the project to have an interaction between human and robots. Robots can act like a professor and to suggest some improve of the play.
That's very interesting.
That challenge can be very interesting.
Great. Thank you, Véronique. Thanks for your excellent talk. So this talk has been recorded and the video will be available online soon. Just to remind you that IEEE CIS Webinar Committee invites excellent researchers in computation intelligence to share their research ideas and projects in the webinar series. Please Google IEEE CIS Webinar, then you will be able to find our webpage. On the webpage, you can find a list of past webinars and videos, as well as the announcement of some upcoming webinars. Thanks again for Véronique for this excellent talk, and thanks again for all the audience for joining the webinar today. Hope to meet you in person one day in a conference or another event, maybe in the 2018 IEEE Conference on Computational Intelligence and Games at Maastricht University, the Netherlands. Now I will end the webinar and see you next time. Bye-bye.
Bye-bye. Thanks, Jialin.
Thank you.